So Houlding sort of opened the door for me to use ecclesiastical language by emphasizing a stark contrast between good and evil in her talk. I gotta say, in terms of the sort of spectrum from Voltaire on one end and Leibniz on the other, I know we're in the Newton Center, so don't Hillary me. I'm kind of more to the Leibniz side, so instead of the agatho-cacological spectral sequence, mine would be more agatho-agatho spectral sequence, or if you prefer, Agatha all along. So, and now I'm done with the jokes, good, and I have plenty of time. So I want to talk today, I want to pay a bunch of debts that people ascribed to me. So I guess I'll get started. In that last time, I talked about G-commutative monoids. Last time. And, there we go. G-commutative monoids, and I focused on a particular case, and I showed that if I looked at the G-commutative monoids in coefficient systems for G, then I got the category of Mackey functors for G. And you can think of a lot of Clark's talk as actually being a prolongation of this statement to actually the topological context. Everything I talked about was just an algebra statement, and then Clark described how essentially the same thing is true if I'm working if instead of coefficient systems of sets, like I was doing, coefficient systems of spaces. And then I would be seeing on this side the spectral Mackey functors. And again, my commutative monoids are not necessarily group complete. They're just commutative monoids. And so here I would be getting the really something closer to GE infinity spaces, so not necessarily group-like ones. But I want to talk now about the multiplicative version. So Tina described the multiplicative norms. And so what I want to do is give the algebraic version of these. So I have norms, and these go from Mackey functors for H to Mackey functors for G. And then the upshot is I'm going to end up at a story saying that when I use these in place of co-induction, and as Tina also pointed out, I have a symmetric monoidal product that's traditionally called the box product on G Mackey functors. And if I consider the G commutative monoids here, then I get what are traditionally called Tambara functors. And so I want to continue to use this. I like to think of this as sort of the external formulation, and we'll see that it actually buys us a few computational things that are a little easier than the traditional version, which sometimes people attribute to a lot of different people, but I'm going to attribute to Tambara, because he really spelled out a lot of the framework. So let me unpack the two pieces here. So here's like the quick definition for both of these. For the box product, I'm going to use the diagrammatic approach where Mackey functors or product-preserving functors out of that Lindner category that I described, the correspondence category for finite G-sets. And then I have a Cartesian product that takes me from the spans of finite, that takes me from finite G-sets to finite G-sets. And then I also, if I start with a pair of Mackey functors, well, this went over into set, where I'm going to just evaluate each of my Mackey functors on the two coordinates independently. So this gave me and you can check, this gives me a product-preserving functor, and I can left con extend. This is the box product. And I wrote it this way because I can, in basically the same amount of space, describe the norms, and this is due to Hoyer, and then also Buch described this, and Mazur, that if instead I started with an H-Mackey functor, then instead of, I start with the Lindner category for H, and I can now co-induce up. And this takes me to the Lindner category for G. And the important part about both of these is I need to check that this actually gives me a functor. Well, I'll put cross here. I need to check this gives me a functor, but the composition in my categories were pullbacks, and pullbacks are limits, and those commute with things like products and like right adjoints, like co-induction. So it's not hard to check that I actually get a functor here. It doesn't take disjoint union to disjoint unions. In fact, in some sense, that's the hard part of all of this story, but I can still left con extend along it. And that is product preserving by a result of counting lack. And that's how I'll build my norm. And this is what played a role in what Tina was talking about, that I see this sort of algebraic description. Now, I guess my job is actually to be a topologist. I like to pretend that I'm just an algebraist, so I'll give the topological versions of both of these too. In this case, the norm in Mackey functors is actually the same thing as taking the pi 0 of the norm in spectra of the associated Allenberg-MacLane things. And so if you start essentially with the right-hand side almost as a definition, then you can reverse engineer the left-hand side, where I start with how would I present a Mackey functor via Friese, and then the norm commutes with sifted colimits. So I write something down as a nice enough co-equalizer. For this one, I have yet another description that I can give, and it'll let me talk about what the commutative monoids at least are. So a commutative monoid for box is sometimes called green functor. And the structure I see here is the following. I have, for every orbit, G mod H, I have a commutative ring. And if I have a map of orbits, so from G mod H to G mod K, then I'm going to get a couple of things. The first I'm going to get is I'll have a restriction map that's a map of commutative rings and then I also have a covariant map that's my transfer. And in this case, my transfer isn't a map of commutative rings, but it has the property that since I have a commutative ring map from R of G mod K to R of G mod H, R of G mod H is actually a module over R of G mod K, and this map is a map of R of G mod K modules. And then I have my double coset formula. So I had an underlying Mackey functor, and then this is describing for me how the multiplication works with this. Another way that I can think about this is sometimes called Frobenius relation. And that says that if I multiply some element times a transfer, then this is the same thing as a transfer. of now the restriction to h of A times B. So I can just, it's another way of saying that the transfer forms an ideal, but actually in this kind of strong sense that all the transfers themselves are giving me kind of an ideal condition. This is just really a restatement of that one, because this is how I defined the module structure on R of G mod H. Now because of this, I can give a different way to think about this. So my box product, heuristically, is first, forget to coefficient systems. Second, form the level-wise tensor. Then form the free Mackey functor on that. So formally put in transfers. And lastly, impose the Frobenius relations. And so I learned this approach from work of Gauntz-Lewis, who sort of described this for CP to the n, where you see that all I do is I just tensor the pieces together the way I would think, sort of, I try to avoid words like naive because of the judginess, but so maybe I'll say optimistically, to continue my earlier metaphor, candidly, then y'all knew I was coming back to it. So, and that's how I would form the tensor here, but then I have to remember that if I actually have a Mackey functor, I need to describe the transfers. So the way I do it is to initially just formally put them in, and then I identify the stuff that I had before with the stuff that I actually want. And you can, and anyway, you can check. All right, so now I want to actually start building sort of more interesting things. So let me state the theorem first. And that is that G-commutative monoids in Mackey functors with the G symmetrical structure given by the box product and the norms, these are the same thing as Tambara functors. And as an aside, which will be a lengthy aside, what is a Tambara functor? That's a second debt I had to pay. Thank you, Tina. And so there's a couple ways to say this, and on the one hand, I might say use this as the definition, because from this perspective, it's a green functor R plus maps of green functors from the various norms of R back to, oops, I should have restricted, excuse me, back to R itself. And they're supposed to restrict in the expected way. And if I combine the norms, just as I did on Wednesday, let me just call this the K mod H norm for R, and then I'm mapping the K mod H norm for R back to R. And I run this over all pairs of subgroups. So if I unpack this, then I get a bunch of conditions. And let me unpack it a little for CP. So if I unpack it for CP, then the additional thing I get here looks kind of like what Tina called the bit vectors, but I would call the universal deformation to characteristic 0, obviously because it's easier to say. And you actually know why I would prefer to call it that, but I also promise not to get too political. so I'll only do so obliquely. So what do I get here? I get the following structure. Namely, I have a commutative ring for the fixed points. I have a commutative ring for the underlying, and I have an action of CP on this via commutative ring maps. I had my restriction map that was a map of commutative rings. I had my transfer map that took me back and factored through the orbits for the Weyl group action. And the restriction landed in the fixed points of the Weyl group action. And then I have one more piece of structure, and that's a multiplicative norm map. And the conditions that I see are that when I take sort of either of the two pairs of morphisms that could look like a Mackey functor, then I get a Mackey functor. So this with res and transfer is a Mackey functor. This with the restriction and the norm is a semi-Mackey functor. So it's a G-commutative monoid, or if you prefer, in coefficient systems, using the multiplication. And then there's one weird condition that I want to write out. And the weird condition is, how does the norm interact with the addition? And it's that the norm of A plus B is the norm of A plus the norm of B plus transfer of a mess. I don't need the exact formula for mess, the frowny face, but I will show you how you can derive this formula. And the thing that I actually needed about this was the first half of this, that the norm of the sum is the sum of the norms, but then there's an error term, and the error term is in the image of the transfer. So modulo transfers, just as Pauling was working, we see that the norm is actually a ring homomorphism. And that's going to be something that's important for us in a minute. So then, where does this come from? And this is Tambara's original formulation. Well, he built a category which the category theorists call polynomials. So I'm going to have a category P where, given two finite G sets, S and T, I consider diagrams of the form S, U, V, T. And then I'm going to work up to isomorphism. I don't want to specify stuff. And so the way you're supposed to think about this, and why category theorists call this polynomials, is that I'm supposed to think of S as describing for me my set of variables. And then my map U, I look at all the preimages of each of those variables, just duplicate them however many times each preimage runs. This is now a multi-set of my variables where they show up maybe many times. And then V says, take the variables parameterized by each point in U and multiply them to get a bunch of monomials. And then the V to T says add them all up. So it's exactly a categorification of the process of writing down a monomial with non-negative integer coefficients. So it's a really convenient formulation. I kind of prefer this to what we seem to call them in homotopy theory, bispans, I guess because there's two arrows. But I like the I like the polynomial language because it's really driving home what's happening for us. What I haven't done is describe for you the composition. And so this is where the TNR comes from. I'll call this, if I had F, G, and H, then I'm going to write this as the transfer associated to H, composed with the norm associated to G, composed with the restriction associated to F, T, and R. And the ones where I let all but one of these be the identity, those give me the individual maps, TH, NG, or RF, and I sort of build the free category generated by these, subject to a couple of relations that if we have a pullback diagram, S prime, T prime, S, T, F, G, G prime, F prime. Then I get some, I have sort of two ways to get around this, and I'm not going to remember. Oh, God. This is probably why people use notes. I have two ways to get from the value of some functor here to the value of some functor here. I can do the covariant version, excuse me, I'm being recorded. I also have to watch what I say. It's like weirdly challenging all of a sudden. So I go from S to S prime by the contravariant one. So I'll have R F prime. And then I'll use the covariant one to go from S prime to T prime. So that's T sub G prime. And that's supposed to be the same thing as doing the covariant one along G, followed by the contravariant one along F. This is, I'll move it up. This is when Clark was talking about the sort of the Mackey axiom. It's the Lindner condition that we had that basically says that if I forgot all of the norm maps, if I just remembered the R's and the T's, then I'm seeing a Mackey functor. This part. The other thing that I have is I have that if I did the restrictions of the norms, that was also supposed to be a Mackey functor. So I can write the same thing, but replacing the T's with N's. And then the last part is the one that you've been anticipating with bated breath, because I have one more pair of things to tell you how they commute past each other. And then I'll be able to put everything into a standard form, namely TNR. And so for that, if I look at, I don't want to do this. Yeah, there's no way to do it except this. So if I look at finite G sets, the sliced category over T, and I look at the sliced category over S, and I have a map from S to T, F. Then I have a pullback map that takes me from finite G sets over T to finite G sets over S. One of the really nice categorical features about this is that the pullback has both adjoints. It has a left adjoint that we call the dependent sum. You might also call this post-compose with F. And which I think is a little easier to think about. And then I have the right adjoint, which is called the dependent product. And you should think about, the reason this is called the dependent sum is I take all of the fibers and I take the disjoint union of all of the fibers over I sort of work here, take the fibers over it and sum them all up. In this one, I take a point here, I take the fiber under the map F, and I multiply together all of the fibers over it, hence that dependent product. So the dependent product fits into an exponential diagram, and it's just one that looks like I have S, I have T, I have U, and so this is some G and F. I form the dependent product here of U, that sits over T, and then I pull this back, cross over T with the dependent product. And here I'm going to have, let me actually, sorry to do this, let me change the name here. I'm going to hate that in just a second too. It's going to make sense in a second, trust me. So let me name these. And now the last condition is that if I did the norm along G and composed with the transfer along H, so the other order to the one that I wanted in Tambara's nomenclature, TNR, this is supposed to be the transfer along H prime of the norm along G prime of the restriction along F prime. That's it. Super simple structure. Really easy to work with. The nice thing about it is this dependent product, it actually looks really confusing when you first start working with it. But the key case for the dependent product that you actually want to think about, because I'm looking at maps between finite G sets. If I'm mapping to a finite G set, then all I have to do is break that finite G set up into orbits. Now I'm mapping to some orbit. I have an equivalence of categories between G sets over G mod H and H sets. So this tells me I might as well have assumed this was a point. And so here are the two cases. If I did point, and then G mod H, and then the fold map, G mod H disjoint union G mod H. Ooh, I did not leave myself enough space. So I had point, G mod H, G mod H disjoint union G mod H, and this is just the fold map. Well, what I didn't say right here, because I'd said it on Wednesday, is that when I apply some product-preserving functor to the fold map, that gave me the addition. So I should think of this diagram as encoding for me. So the norm associated to this quotient, composed with the transfer associated to the fold of some pair, AB, is actually the norm from H to G of A plus B. So I wanted to understand, like that formula that I wrote over there, together with the frowny face, how do I do this? Well, this is one of the two cases I need to understand what the dependent product is, and it's actually co-induction. It's the H maps from G into the 2-point set. If you haven't seen the dependent product, do this example and the next one, and you'll understand everything that you need to know about the dependent product. So it's not a surprise somehow that I keep running into co-induction. It's the thing that it showed up additive for us. It described the entire additive transfer story. And then when I take infinite suspension, it's describing for me the entire multiplicative story. And so we're just going to keep running into it. And when I do my last pieces, you can then use this. This is basically it works out to evaluate. I should think of these as sections, and then I'm evaluating my sections at various points. Then you can completely write down the formula, because I need to understand what are the orbits that show up here, and how do I break it up into pieces. So that's the first. Oops, forgot. And here's the second. If I did G mod H, again goes to point, and then it came instead of from the fold from some G mod K, and this is just the usual quotient map. Then here I'm describing a different relationship. I'm describing what's the norm from H to G of the transfer from K to H of A. And the dependent product in this case is again co-induction. But now I map G into the H set, H mod K. And here I have G mod H cross them. Because I was mapping over point. So somehow everything, this is extra sad. Everything that I would want to know about this is entirely encoded in these two diagrams, together with then understanding the combinatorics of co-induction. Okay. Now when I think about these as the G-commutative monoids, though, then I can, just as last time, talk about things like a tensoring operation over finite sets, or finite G sets. So I get that, that my G Tambara functors, which I was writing, I guess, as Tam G, I wasn't using the Bowman convention, then these, I have this tensoring over finite G sets. It's not how I write a tensor symbol. Where basically, if I did G mod H, tensor my Tambara functor R, then this is just the norm of the restriction. And this norm here, this is left adjoint to the forgetful functors from G Tambara functors to H Tambara functors. So again, I've automatically built a coefficient system of sets. So when I look at the maps of Tambara functors from R to S, this is really, in fact, it's canonically the value of a coefficient system of maps of Tambara functors from R to S at G mod G. And I can think of the value at G mod H in several different ways. And the simplest is to say, well, just forget. Just take H Tambara maps from the restriction of R to the restriction of S. And the property of being a Tambara functor told me that I could understand I could rebuild this by instead using that IH upper star had a left adjoint, and so this was the same thing as staying entirely in the context of G Tambara functors, but now doing the G mod H norm of R and sending that to S. So again, the covariant assignment that took T to T tensor R gave me a conjugate assignment on Hom out of R in a functorial way in R and in a functorial way in S. So really, I don't want to think of this just as a set, and I'm going to keep driving that point home for the next, I don't know how long. If there were anything that I were to call evil during this talk, you know what, I can't because it's a choice. And I'm all about personal freedom for other reasons that you're going to know, that you know. So the thing I want to stress is that when I'm talking about equivariant objects, I want to think of them as being enriched automatically in G sets or in G spaces, not as being just the equivariant maps. And it's sort of forced on us when we remember that we just have more structure automatically in the category. That the moment I take seriously that statement, it comes for free. And now I want to erase, and I'll pause for questions while I'm erasing. Dramatic pause. And yes, I'm singing the Macarena in my head. That was for you, Magdalena. I keep forgetting this is recorded, and I'm going to I thought that if I didn't respond to their email saying, "Do you consent to being recorded?" that the default would be no. But it turns out they've dealt with mathematicians before. So fuck. That's my one swear that keeps us at a PG-13 rating. Okay, so what I want to do now is I've started to build this context, and I want, there's two things I can do from here. The first is I've talked about how I'm automatically tensored over G sets. So what I can do is I could instead consider simplicial Tambara functors, and those are automatically tensored over simplicial G sets. And the nice thing about the notion of the G-commutative monoid is it's kind of robust in that simplicial G-commutative monoids are the same thing as G-commutative monoids in simplicial things. So if I consider simplicial Mackey functors and did the level-wise tensor and the level-wise norm, simplicial level-wise, not G mod H level-wise, then the G-commutative monoids for that are the same thing as simplicial Tambara functors. So I get this additional externalization, and I can use that to then try and build some invariants. But I want to talk about a very closely related, but slightly different approach that you can think of as André-Quillen homology. And so I had to get to stabilization eventually. The unstable there is obviously referring to me, but it's also referring to the fact that here, when I did an enrichment, if I did the simplicial enrichment, or the G-simplicial enrichment, then my collections of map-student Tambara functors were giving me a G-space. That's what Elmendorf's theorem tells us. Well, Elmendorf's theorem, together with the Quillen-Kahn result, that simplicial sets and spaces are the same thing. I'm not going to call them anima because I'm not a Jungian, and I'm sufficiently comfortable with my feminine side already. Look it up. So instead, I'm going to talk about, you're welcome. Instead, I'm going to talk about how do I build things like abelian groups, modules, and then sort of set the stage for how I would do the full cotangent complex. And time permitting, which I'm definitely running out the clock on by pacing back and forth, I'll describe exactly how to do equivariant topological André-Quillen homology. Okay, so the thing that I want to do is start with an anecdote. I told you I was running out the clock. I don't know why you laughed. So early on in my learning about Tambara functors, I was deeply influenced by Strickland's memoir. And I definitely recommend reading it. He proves some things in there that can't be found anywhere else. It's really spectacular work. There was one part where I didn't completely agree with a definition. And that is, and I'm going to make the definition, and since I'm giving the talk, not Strickland, I'll give the definition that I gave. So if R is a Tambara functor, then an R module is just an ordinary module in Mackey functors. Over the underlying green functor. So I gave this as my definition, and the reason that I gave this as a definition is I was thinking about the G-commutative monoid approach, in which case you may be familiar with what's sometimes called like Tanaka duality or like a Tanaka reconstruction, where if I have a symmetric monoidal abelian category, then I can rebuild the ring if it's the category of modules over some R, I can rebuild R as the endomorphisms of the symmetrical unit. So I didn't need to know what R was to know what the category of R modules was, the other way around. I didn't need to remember what R was if I knew that it was R modules. And so from this perspective, there is a version of that sort of Tanaka reconstruction where what I have to do is I have to remember this category of R modules, but it inherits norms. It inherits a full G-symmetrical structure, and I can use those to rebuild the G-symmetrical structure on R, and then I can use that to rebuild R as a Tambara functor. So this, as a G-commutative monoid in categories, gives me R as a Tambara functor. Now, on the other hand, this is also, as Strickland put it during my talk, not the right definition of an R module. And Strickland was right. And I was right. So there's this sense, and this is why I'm going with the it's all good, there is no evil, because, which is also an obvious lie, because it is so hard not to get political. Thank you. I feel like totally validated, thank you. I'll wait to rant about Nazis until the end of the talk then. So here I have my Tambara functor, and what was Strickland's definition instead? So a module a la Strickland. And this actually very closely hews to the André Quillin story. I have the category of augmented Tambara functors, augmented down to R. So Tambara functors augmented to R. And I have a Yoneda map that basically says, given a Tambara functor S, I can map into one of these. So I get the Yoneda embedding that goes from Tambara functors augmented to R into presheaves of Tambara functors. Ooh, this is going to get long. Augmented to R. And I'll call this H sub something because I'm doing the covariant one. And it just takes me to it takes S to the function that takes some B to maps of Tambara functors over R from B into S. Now, here I have products, and these were presheaves of sets. So I can play the usual game where if I have a presheaf of sets, I can ask for a way to lift this from a presheaf of sets to a presheaf of abelian groups. So sitting over this, I had functors from, oh God, there's so many letters, up into ab, and then there was a forgetful functor. So I can ask, for some given R, is there a way to lift to this? And what conditions does that put on R? What do I need to produce, or sorry, not on R, on my S. And so some of the things we see pretty cleanly. The fact that Tambara functors has products tells me that I have most of the structure I need. So essentially by the Oneida lemma, this functorial lift of H sub, what do I call it, S to AB is the same data as, well, saying S is an abelian group object in the category of augmented Tambara functors. So I have a map like this, that's my addition, and I have a unit, which is just a map from the terminal object back to S, and these have to satisfy the conditions of being an abelian group. Now, the second condition tells me that S is actually not just a Tambara functor augmented to R, it's also an R Tambara functor. It receives a map from R. And so that means I can split off the augmentation ideal sitting inside it. So this part tells me that S breaks up as R direct sum I. And in fact, I can deduce that I is a non-unital Tambara functor. Now, if you don't know what a non-unital Tambara functor is, well, remember, at the start of Wednesday, I pointed out that if I just considered finite sets and epimorphisms, then I got non-unital commutative monoids. So play the entire game that I did for Tambara functors, but only allow that map G to range over epimorphisms. And that's a non-unital Tambara functor. Alternatively, it's a Tambara functor that doesn't have a 1. It's like, I guess I should have said that instead. So the condition that I'm an abelian group object is the condition that my multiplication on I is 0. So abelian group means that the multiplication as a map from, I box I back to I is actually the 0 map. And this is the thing that Quillen showed, and it's how I build, if you've seen this, it's how I build the ring of Kähler differentials. I take the multiplication map, I take the kernel of that, and then I take I mod I squared, and this is my ring of Kähler differentials. It's exactly the same story, and I've built something where I have a multiplication that's 0. So this is Strickland's definition. So secretly come back here. It's abelian group objects in Tambara functors augmented to R. Now to pull all of this together and to make my statement, we were both right even though we're saying radically different things, actually mathematically precise, I want to stress that again, this is actually the same thing as coefficient systems of abelian groups on augmented Tambara functors over R. And so now I'm primed to say, oh, well, literally the entire point of the 2 talks I've given is anytime I see a coefficient system of things, I need to build the corresponding Mackey objects. And so the difference between these two definitions, so R mod itself in the version I've given is just the G-commutative monoids here in Strickland's version. Or if you prefer, it's the Mackey functor objects in Tambara functors augmented to R. Now, to give you a sense of how this works, I wanted to spell out a little bit about how these two things are actually genuinely different. And I mean the genuine here, not in the sense we've been using it in equivariant homotopy, but in the standard English use of the word. That these are actually, they're actually different. So let's look at what happens for CP. So these conditions, they told me that I had some I, and I had the value at CP mod CP, and that was a ring that was non-unital, and the product was 0. And then I had the same thing for the underlying. It's a ring. It's square 0. I have a CP action. And then I have my transfer. So this looks a lot like saying that I have an R module, because I have the same pieces. What I still had, though, is I still had my norm. When I pass to kill all quotients, or excuse me, kill all quotients. When I pass to kill all products, I just killed the multiplication. I didn't kill this additional structure. So now I have a condition, and the conditions look like that if I restrict the norm of some A, this actually is 0. And then other conditions that come along somewhat surprisingly are the norm is multiplicative, is an additive map, and the norm is a map from, in fact, an R of CP mod E module to R of CP mod CP modules. Both of these are really unexpected from the point of view of one of the axioms that I think I either wrote here or just above it, that the norm of a sum was, well, the sum of the norms plus some error term. But that error term involved multiplications. And I'm in a context where all multiplications are 0. So I don't even have to worry about it. On the other hand, just having an R module, well, an R module, I don't have the data of a norm. So the moment I write down something like this where I have a norm, I see a difference between the abelian group objects in augmented Tambara functors down to R and Mackey functor objects. Okay. Now I want to say something weird. I'm going to go sort of increasingly off the map at this point. I'll do it in this order. So now I want to return to topology. This is a topology conference, so I'll sort of, if I can end there, then I can pretend to have given a topology talk. So what are the analogs of all of these pieces? So in this case, I'm going to give myself, as a bunch of people have used, now R is going to be, we'll call it a GE infinity monoid, a GE infinity ring in a genuine G spectrum. And then I can ask, well, if I look at this is the same thing as COM in any of the standard models, but I want to stick to calling it G-commutative algebras augmented to R. This is now a category that's enriched in pointed spaces. I should say, it's enriched in pointed spaces when I did the ones that are also R algebras. But this is the topological version of this, the Tambara functors over R. The topological version of abelianization is stabilization. So out of this, I can form spectrum objects in G-commutative monoids over R. Now there's this amazing result of Bastera-Mendel if it's not equivariant. And what Bastera and Mendel show is that if I take augmented R algebras and I stabilize, then this is the same thing as just modules over R. And so that's what I would want to happen here. But the algebra tells me that can't happen here. The stabilization, if I did pi 0, the stabilization is building abelian group objects. It's not building Mackey functor objects. So this is some stable infinity category, but it's not R mod. What I can do instead is I can form genuine G spectra. Genuine G spectrum objects built out of G-commutative monoids over R. So I stabilize now not just using trivial suspension, but I've inverted all the representation spheres. And here you do get the Bastera-Mendel result. This is R mod. And there's two additionally surprising features here. One of which is, when I had Tambara functors, these were different. And you can see I'm actually describing an entire hierarchy of things between these. On the one hand, I had no transfers. I had coefficient systems, and that's just what Clark had talked about, where if I took coefficient systems with spaces and I stabilized it, I didn't get genuine G spectra, I got the stabilization of coefficients of spaces. On the other hand, I could do the equivariant stabilization, and then I end up getting the thing that I might have hoped. I get R mod in the end. If I added an intermediate number of transfers, then I get stable infinity categories that are going to interpolate between these. And it's kind of weird. And the really weird part is if I did this all without any transfers. So if I just did this in green functors, or in not G E infinity things, but in just ordinary E infinity monoids augmented to R, then these automatically collapse down. They're all the same. The stabilizations agree. There's something about the interplay between the presence of the norms and the kinds of representations or the kinds of transfers that I'm stabilizing with respect to. And you see it in both cases. Now I've got 57 seconds, and that's just enough time to, as I promised, talk about Undrick-Quillen cohomology. Pardon? Oh. Y'all are trying to get me banned from this place. Undrick-Quillen. Get thee behind me, Satan, to come full circle to the ecclesiastical language. So Undrick-Quillen homology says that I have an abelianization functor that goes from augmented Tambara functors back down to either the abelian group objects, that's the cotangents, omega 1, and it goes, I have a further one that takes me down to Mackey functor objects. And if I think of what's omega 1 doing, well, I'm supposed to take the kernel of the augmentation, and then I kill all of the products, that's omega 1. To get the genuine omega 1, the one that gives me Mackey things, I kill all the products and all the norms. So I see I have a hierarchy here. Now the thing that I want to end with is the property of one of these being 0 is equivalent to all of these being 0, no matter what collection of norms I put in. So if I think of a tall as being built out of something like omega 1 vanishes, I guess it's actually like smooth or something, I don't know. I'm not an algebraic geometer. Then all of the notions of omega 1 that I can write down, the vanishing of all of them is equivalent. So there's something that's radically collapsing in a way that I do not have language to describe, in part because I'm not an algebraic geometer, and in part because I don't understand how I'm supposed to interpret this like uniqueness of a tall in this case. All right, that's a good place to stop. Thank you.
Questions, but I'll ask one. I remember you mentioned Tanaka type reconstruction.
Yeah.
Is this literally known, like that you can construct a Tambara functor from its modules in the sense of like equivariant stabilization or Mackey functor objects?
It depends how you define literally known.
Okay.
So I believe that in the stable infinity category context, I think that J. Shaw did that. In just the algebra context, you just write it down. And the same way that you write down sort of the original arguments. So that's my prevarication.
Other questions? So why are the Italians things the same? Asking for a friend.
That's a great question. You know, that's the kind of question that normally I would go to Birgit and ask, hey, I'm noticing this really weird phenomena. And since you think about these things in like a much more nuanced and like robust way than I do, I don't know. And I think it's very confusing to me. But the argument's not hard. And that's what's even more confusing. That the genuine omega 1 is a quotient of the trivial omega 1. And so the vanishing of the trivial omega 1 then necessarily implies the vanishing. But then all of the pieces that I'm quotienting by to form the genuine one are inductively the lower, in the subgroup lattice lower omega 1s. And so I write down a bunch of little exact sequences where then it's if I have a group that's an extension of two zero groups, then it's also the zero group. And so I don't know how I'm supposed to interpret that, but it's telling me somehow that there are simultaneously more étale maps than I would think, because it's a green condition, and maybe less étale maps, because it's a Tambara condition.
There's kind of an analog between THH et al. And TAQ et al. I mean, SO2 et al. And
Yeah.
commutative et al.
Yeah.
But then there's one implication, there's a convergence question, which requires some sort of boundedness in those situations. This is
Right.
finite groups, there's probably not a
Right.
convergence issue.
Right. The full argument does just, you work up the subgroup lattice. And then, yeah.
So, okay, so this argument shows that the two guesses that you could make for what étale could mean coincide.
Yeah.
But that's not true. Is that true for a Zariski as well? Like when I think about the meaning of a Zariski open immersion.
Oh my gosh, I am so glad you asked this question. No.
Yeah.
No. That it turns out Zariski opens, or like what the same question is, what does it mean to invert an element?
Yeah.
And if I have a Tambara functor and I invert an element, then I might worry, because I've got this diagram of rings, so I have to ask, like, where does the element I'm inverting live? And then I have to, that's the first thing I ask. And it turns out for a Tambara functor, I can always assume that it lives at the very top level, at R of G mod G, at the fixed points. And then it just propagates down to all the others. Because it's that usual thing that if I invert something, I actually invert the multiplicative hull of that something. So what do? I norm it up to the top, and then I invert that, and then it propagates down through everything. In just green, or if I didn't have that norm, I get really weird things. And I don't even know how to write them as, say, filtered colimits of the things that I'm starting with. Some nice diagram of just the underlying modules. Whereas with Tambara things, This is how you see that it like preserves flat and things like that. The green, it doesn't even preserve flat. So it's weird. It's very weird.
Yeah, you mentioned you're not an algebraic geometer, but is there a way to define algebraic geometry in this context, like the spec of a Tambara functor?
There are a lot of people who've thought of that. And it is too late in the week for me to remember anyone's names. So I would, oh God, thank you. My student Ben. Ben, don't watch this video. YouTube block his account. So Ben, JD, Danica, and I think David Chan were all involved in looking at a version of this, and there are lots of approaches for how you might do it. And somehow the hard part is something that Lars Hesselholt pointed out to me. We don't actually know how to define a local ring in this context. And so one of the easiest ways to do this is to look at some kind of functor points approach, but I don't know how to define the basic test objects. So I'm kind of stuck.
Other questions?
Yes, I have a question. So,
Yeah.
I think one of the preferred things to do with TAQ or with Andre Quillen homology is do deformation theory.
Yeah.
And by doing
Yeah.
so, compute some zero groups.
Yeah.
Can you compute?
No.
Okay.
Your question is exactly what I would like to be able to do. Even in algebra, I am stuck almost from the get-go because, like, how does Quillen actually do this? And this is why I got very disheartened. And so how does Quillen do this? Well, this is actually one of the reasons why Quillen developed model categories. So I love sort of being able to invoke the early stages of the field. He built model categories because he wanted to understand cohomology theories and deformations in associative algebras. And so he needed a way to homotopically deform these. And so he built, and one of the key example he builds at the end of his book is a model structure on simplicial commutative rings. And he's doing it so that he can actually make sense of Andre Quillen homology, or in this case THH, but like the associative version, where what I do is I replace my thing by a cofibrant, which has the property that it's basically, I can choose it to be polynomial rings and like work my way through in some really nice way. Polynomial rings are all flat, I tensor these together, I get all the sequences I want, and I get everything I want from my homology theory. So I said, great, I can do this, I have this definition, let me start. And that very first step of starting with polynomial rings, great, these are frees. The very next step, polynomial rings are flat, is never true. Almost never true. There's at most one case. There's at most one case for a given like incomplete Tambara functor that it could be true. And then you're kind of stuck. So I think the solution for that is actually just to drive everything to do n-infinity algebras in simplicial Mackey functors. But I don't know how to compute anything there either.
So you said there's a stabilization. Do you also get a Coulomb description, like higher and higher representation spheres tensor this thing?
Oh, for this one? Yeah. That I could view it as like sequences of things where I have maps from tensor with the regular representation sphere. So I'll run my sequence like that.
So you get some low degree classes probably from THR calculations and other things you.
I'll be very happy for you to explain that to me.
Ah!
Thank you for volunteering. And it's recorded, so I'm never going to lose that code.
Any other questions? Okay, then let's thank Mike again.